Welcome to the third and final instalment for November 2020 Edexcel's Maths Higher Tier papers. So this is the last one of three. It's calculator all the way, so in some ways that makes it easier, in other ways not obviously so. So let's have a look at how these questions work and the solutions to them. So we'll start straight of all, get to it with question one. So for question one, we need to just simplify some of these algebraic expressions. So the first one is n cubed multiplied by n to the power 5. The most important thing here is when we're multiplying terms with the same base values and they have powers attached, we can just add these two little numbers together. So n cubed plus n5 times n5, sorry, we just do 3 add 5 to give us 8. So the first one is just n to the power 8. In the opposite way, when we're dividing terms which are the same with powers, we simply subtract one power from the other to get the new power. So thinking of the c's first, c cubed divided by c squared would be c to the 1. And the d's, d to the power 4 divided by d, which is the same as saying d to the power 1, that would be d to the power of 4 minus 1, which is 3. Now with algebra, you don't need to put the power 1 on things, so this can be fully simplified by not needing to write that 1. So the final answer is just to write that c on its own, then d cubed. So 1b, we've got c d cubed. For c, we need to solve an equation. There's a few ways of doing this. What I'd tend to do is think of it as an equation. You might be thinking, but it's not, it's an inequality. True. But think of this as an equals and solve it in the same way you would any old equation. So imagine it was 5x over 2 equals 7. Our objective, what we want to do, would be to have x equals, and that would be our answer. But at the minute it's tied up with that 5 and that 2. What I'd suggest to do, first of all, would be to get rid of this 2. So what is the 2 doing to the 5x above? It's dividing. Opposite of dividing by 2 would be to multiply by 2. That's how we'd get rid of the 2 here. But if we perform this operation on the left-hand side, we need to perform the same operation on the right-hand side. So we must do 7 multiplied by 2, which should give us 14. So the next line is 5x equals 14. Then to get x on its own, to go from 5x down to x, we'd have to divide by 5. But once again, if we divide one side by 5, we need to do exactly the same thing to the other side. So then we'd have x equals 14 over 5, and that would be a perfectly valid answer. The only thing would be to remember, absolutely remember, that the actual symbol wasn't an equals, but was this inequality facing this way. So your final step, you must remember to get rid of the equal signs and put back in the original symbol we were dealing with. So we just need to go like this, and like that. So the answer is x has to be greater than 14/5, which is also fine if you write x greater than 2 4/5, or if you're a decimal person, you could have also put x greater than 2.8. So either 1, 2, or that answer is validly written in terms of how to solve it. So that's all of question 1 done. Let's now move on to question 2. Question 2. So Andy cycles a distance of 30 kilometers at an average speed of 24 kilometers per hour. Afterwards, he then runs a distance of 12 kilometers at an average speed of 8 kilometers per hour. So it says here to work out the total time Andy takes. So we're asked about a time, we're told about distances and speeds. So what relates distance, speed, and time? Well, it's speed equals distance divided by time. And that relationship can be put into a magic triangle like this. Speed at the bottom, distance over time. And the good thing about these magic triangles, as I call them, is whatever you want to work out, you just cover up with your hand. So because we want to work out the time, just cover that up, and what's left tells you what to do. So, in other words, the time is the distance divided by the speed. So I can write that down because that's what we're going to be needing to use here. So we're told that the distance is 30 kilometers for his cycling and then running. And again, we know the speeds at those points. So what we need to do is think of this as two separate parts of a journey. So for part one is when he's cycling. So cycling, the time he takes cycling is the distance he cycles divided by the speed when he's cycling. So the distance is 30, wrong colour, distance is 30, and the speed that he's cycling is 24 kilometers per hour. Kilometers here, kilometers there, the units are consistent, so we can just go ahead and perform the calculation without having to worry about changing the units or making errors in that way. So we just need to do here 30 divided by 24 and press equals 5/4 or 1.25. So that time, because our units were hours going in, hours are going to come out. So cycling was 1.25 hours. The second part of the journey, though, is when he's running. So when he's running, the time taken for his running will be the distance covered by his running divided by the speed at which he runs at. So let's just put these values into this formula again. So the relevant distance when he's running is 12, and the relevant speed is 8 for that part of his journey. So we're going to do distance, which is 12, divided by speed, which is 8. So if you want to calculate that, 12/8, that's going to give you 1.5. So 1.5 hours running. So we want to know the total time he takes. So all we need to do now is to add together the time taken from the cycling, which is 1.25 hours, and add to that the time he spends running, which is 1.5 hours. So 2.5 plus 1.5. Again, by all means, please do use your calculator. But you should get there 2.75. 2.75 hours. But you need your answer in terms of hours and minutes. So we need to think about this in terms of how do you deal with a 0.75? What's 0.75 of an hour? Well, there's two main approaches in my mind. One is a harder way, one's an easier way. I'll give you the harder way first. 0.75, if you knew that's 75%, that's the same as 3/4. So the 0.75 means 3/4 of an hour. 1/4 of an hour is 15 minutes, so 3/4, or 0.75, must be 45 minutes. So you could reason that this is 2 hours 45. That's what you need practice in as a skill in itself to find that easy, I think. A much easier way, which you might not know about, is the calculator can actually do this for you itself very nicely indeed. I'll show you how. So the decimal number you want to change into hours, minutes, or even hours, minutes, seconds. You type in the decimal number first, and then just press equals. Now on this particular Casio, there'll be a button like this, which looks like a little degree circle, then an apostrophe, and an apostrophe or punctuation marks. This weird looking button there is what you press next. It'll change this number here into hours and minutes. So press this, and you can see it gives you 2 hours, 45 minutes, 0 seconds. So it's exactly 2 hours, 45 minutes. So that's what we need to write down for our final answer. So in terms of hours and minutes, we've got 2 hours and 45 minutes. So that's all we need to do for number 2. Question 3, we have a number, m, which has been rounded to 1 decimal place. The result's 9.4. Complete the error interval for m. So let's just take this step by step. First of all, rounding to 1 decimal place. So imagine the 0.1 decimal places times table. Okay, the values would be going up in 0.1s. So the 1 decimal place pattern would be 0.1, 0.2, 0.3, 0.4, 0.5, and so on and so on. So getting up towards 9.4, you can picture that part of the number line as being this. So the number line given to one decimal place around 9.4, I'd have 9.4 in the middle and 0.3 and 0.5 to either side. But it's got to be closer to 9.4 than to 9.3. So if we drew imaginary lines in between these one decimal place numbers, we can imagine that 9.4 would have to be between this line and that line. So in other words, 9.4 could not be any lower than 9.35. This is therefore the lower limit. If it were 9.35, it would round to 9.4, but not if it were any smaller. So it can be allowed to be 9.35. 9.4 couldn't get across this line though to 9.5. If 9.4 were beyond this line, it would have rounded to 9.5, so it can't be beyond this line. If it were on this line though, again, it would round up to 9.5. So it just needs to be ever so slightly before this line here. And there's no limit to what I mean by ever so slightly. You could be within a millionth of a billionth of an inch. So because you could be 9.4999999 recurring, it could be infinitesimally close to 9.45. It's simpler to just put 9.45 in your calculator rather than writing 9.4999 recurring. And you get round that by using the inequality symbol of a crocodile facing that way to get out of saying that it has to be equal to 9.5. You're saying it can be anything up to 9.45, but not including it itself. So based on that, for 9.45, that's the upper limit. You're not allowed to actually be this, but it can be anything up to that. So m needs to be between these two values, so therefore that's your error interval, 9.35 up to 9.45. If you notice as well, if you want a quick trick, if you're rounding to one decimal place or so many significant figures, the upper bound will often look like the number with a 5 stuck on, and the lower bound will often look like this number here, but the number before the 5, just knock one off it. So 1 less than 4 is 3. So you can do these in seconds with practice, but this skill in spotting these particular tricks and patterns, when to use them and when not, does need practice. So with practice, these can be done very well, very quickly, but this is a bit more in-depth to try and get you to understand why the answer does make sense and why it's written as it is. Question 4. This concerns Maisie, who knows that she needs 3 kilograms of grass seed to make a rectangular lawn 5 meters by 9 meters. So grass is sold in 2 kilogram boxes, and she wants to make a rectangular lawn 10 meters by 14. She's got 5 boxes of grass seed. Does she have enough grass seed to make a lawn 10 by 14? You must show all your working. Okay, so grass isn't spread on a line. Grass is spread over an area of grass. So this question, the key to it is knowing that it's going to concern area. So this 3 kilogram grass seed can make a rectangular lawn 5 by 9. So what's the area if it was a square or a rectangle 5 by 9? Well, of course it has to be a rectangle. So this area would be calculated by doing the length times the width. So we'd do 9 times 5, which is obviously 45 square meters. So therefore, 3 kilograms of seed gives you an area of 45. So this seed though is sold in 2 kilogram boxes. So 3 kilograms of seed effectively equals an area of 45 meters squared. How can we work out what would be covered by a 2 kilogram box of seed? Well, what we could do here, we could think about what 1 kilogram would cover. How can I go from 3 kilograms down to 1? I could divide by 3, and if I did that, I'd divide the other side by 3. So 15 divided by 3 would give us 15 square meters. Then we can multiply by 2 because we're interested in 2 kilogram boxes. a 2 kilogram box would be enough to make a lawn of 30 square meters. So each one of our boxes, 2 kilograms, would be enough for 30 square meters. Now Maisie wants to make a rectangular lawn which is 10 meters by 14 meters. So the area she needs is 10 multiplied by 14. So the area she actually needs is 10 times 14, which is 140 square meters. She's got 5 boxes of grass seed. So has she got enough grass seed to make a lawn 10 meters by 14? So we've practically done most of this working now. So work out how much can be made in terms of each box. So we've done that. Each 2 kilogram box is enough for 30 square meters. We now have worked out what area she needs, which is 140 square meters. And if she's got 5 boxes of grass seed, then each box of grass seed covers 30 square meters. So 5 times 30 is 150 square meters. That's what she's got enough to cover. So she has grass seed which can cover 150 square meters, but she only needs 140 square meters. So therefore, the question we need to answer is actually a yes or no. Has she got enough grass to make a lawn 10 by 14? Actually, yes, she does. And if you want to impress the examiner, you could say yes, and then explain she would have enough seed to make 150 meters squared. Or you could say something like she'd have enough spare seed for an extra 10 square meters, something like that. Or just enough to prove you've done this calculation here. So writing the answers to these calculations like I've shown you will be enough to show sufficient working. Part B is a slightly weird one to get your head around. What it says here, first of all, is Maisie opens with 5 boxes of grass seed. She finds that 4 of the boxes contain 2 kilograms of seed. Fair enough. The other box contains 1 kilogram of grass seed. Does this affect whether Maisie has enough grass seed to make her lawn? Well, first of all, we said yes. Okay, so before, based on our answers to part A, we would have said yes, she has enough seed. If after what's been said and done here for part B, we'd still say yes, then we'd say it's not affected her outcome. If we change from a yes to a no, though, our answer for part B would be yes, the outcome's been affected because we've changed from a yes to now she doesn't have enough. So let's think about how much she would have. If 4 boxes did contain 2 kilograms of seed, then 4 times 2 is 8 kilograms, and the other box contains 1 kilogram of grass seed, she'd have a total of 8 kilograms plus 1 kilograms. That'd only give a total of 9 kilograms. So would this affect whether she has enough grass seed to make her lawn? Well, if she only had 9 kilograms of grass seed, what we could do is work out how much grass seed she needs exactly to cover the area she needs, or we could work out how much 9 kilograms of seed would cover. So we can use the table we started here and trying to build up to 9 kilograms. So 1 plus 2 is 3, so I could add these 2 rows here, this one plus that one. 3 kilograms would be enough to cover an area of 15 plus 30, which is 45 square meters. Then to build up to 9, I could just triple this line here I've just made. 3 times 3 would give me 9, and over here 45 multiplied by 3, that will give us something rather bigger. So 45 times 3, if you tried that on a calculator, would give you 135 square meters. That's how much of an area could be made from the seed she would have if one bag only had 1 kilogram rather than 2. But remember, she needs 140. So if this were the case and she only got 9 kilograms, she could only cover 135 square meters, not the 140 she needs, therefore no, she would not have enough seed. So for part A, we said yes, she would, so that would affect her outcome. So wording that can be quite difficult, and I don't think it's an easy question to answer with a very articulate, coherent response. So this is something I've come up with which I think is as good as I could do, really. So you could say something like this. So if one box had 1 kilogram of seed, this would be 9 kilograms of seed in total. This would make 9 times 15, which would be 135 square meters of lawn, but she needs enough for 140 square meters. Therefore, yes, it does affect her, as she'd then not have enough seed, whereas before we said yes, she does have enough seed. Question 5 is a good old honest tree diagram question. So Amanda has 2 fair 3-sided spinners. So the diagram would suggest that they're identical pretty much, so assume that they are identical. And if they're fair, all the sides are even, all the sides are equal, each side will have a probability of it landing on 1/3. So probability of landing on any side will be 1/3. She spins each spinner once, complete the probability tree diagram. So what's the chance of it landing on a 2? Well, there's only one side that's labelled a 2 out of a total of 3 sides. Hence, like I've already said, 1/3. So the chance it does not land on a 2 is the chance it lands on a 1, which is 1/3, or the chance it lands on a 3, which is 1/3. 1/3 plus 1/3 is 2/3, so the chance here needs to be 2/3. And each pair of branches, each place where it forks, always needs to add up to 1. So double check, 1/3 plus 2/3 is exactly 1, so it's following the rules of the tree diagram. For spinner B, because it's an identical spinner, the probabilities are going to be no different for spinner B. So we just do the same numbers again in the same locations. 1/3 for a 2, 2/3 chance that it's not a 2. 1/3 chance of a 2, 2/3 chance of it not being a 2. Part B is designed for us to now use the tree diagram for A to answer B. So using the tree diagram, we're going to work out the probability that spinner A lands on a 2. So spinner A landing on a 2 would be this route here. And it says, so I'll come back to why I've picked up on the word and in particular, spinner B does not land on 2. So once we've landed on 2 for spinner A, the next route we take would be going down here, but does not land on a 2. So what we do here is we've crossed these probabilities, we've crossed 1/3 here, and then 2/3 there. And so what we do, for numbers we go past on our route from left to right, we multiply together to have a probability of one happening and then the other. So I always think of one thing happening and then the other, as the and almost always signifying we're going to multiply the probabilities together. And this is what we do here. So 1/3 times 2/3 on the calculator or otherwise, top times top gives you 2, and 3 times 3 gives us 9. So part B, we've got 2/9, the probability of it landing on a 2 for A, and then not a 2 for spinner B. Question 6, we've got 2 straight line graphs, so one's been given already, and the other has as well. If you notice, these equations here are the same as these that we're going to use to solve. So first of all, 5x minus y equals minus 46. So that's the red line here, so I'm just going to colour this one in red. That's 5x minus y equals minus 46. The next one, y equals minus 2x, I'm going to highlight that in the blue. So in terms of when one equation is the same as the other, when they're solved simultaneously, that relates to the exact point where the lines of their graphs intersect. So where the lines of the graphs of the 2 equations intersect, that tells you the solutions to the simultaneous equations. So the coordinates for x and y are the solutions to the simultaneous equations. So where do these two lines cross? Well, obviously we cross in the middle here, where I've colored it in green. So all we need to do is read off the coordinates of that point. So the x-coordinate is -2, the y-coordinate is 4. So the solution to these equations is when x is -2 and y is +4. So that's how you use the graph to solve them. Part B is a similar idea to Part A, really. So if you look here, we want to use this curve, this parabola, to see when it's equal to 0. And so we've drawn the graph here of y equals x squared minus 4x plus 2. So we want to solve this bit equals 0, but this here is what y is. So we're wanting to see when y is equal to 0, because this expression here is equal to y, and we're wanting to see when it's equal to 0. So logically, we're going to see when this thing here is equal to when y itself equals 0. So whereabouts is y on this graph equal to 0? And then when we know that, when is y equal to 0? And it's the same as this curve. So what we need to do in plain English is just see where the curve crosses the line y equals 0. Now the line y equals 0 is a horizontal line cutting y at the origin. So it's this red line here, right on the x-axis. So you can see this parabola cuts y equals 0 at 2 points here and there. Read off those x values, and those x values are your estimates to this quadratic equation. So using the graph, x equals 0.6 or x equals 3.4. This one's at 0.6. Over here, we've got 3.4. Now, the wording of this question may have really confused you, but if that does happen, please bear in mind, if it's a calculator exam like this one, you could just use a quadratic formula to solve this, and then use that as a bit of a cheat to write down what x could be. So that's my suggestion. If the wording of the question confuses you, just solve it using the quadratic formula. So you'll get two values of x, so just guess that's when the answer to when x squared minus 4x plus 2 is equal to 0, and you'd get some credit, I do believe anyway. So that's a way of trying to think around the problem if you're having an emergency or a panic. Question 7. There's a total of 45 boys and girls in a choir. So we're talking about mean ages of the boys, mean ages of the 27 girls. Calculate the mean age of all 45 boys and girls. So we need to remember the formula for the mean. The mean is the total of all objects divided by the number of objects. So adapting that idea here, the mean age is a total of all ages divided by the total number of people. And we can put this into a formula triangle. So mean age is total ages divided by the total number of people. So obviously we've got two different groups of people. We've got boys and girls. So think of it in two categories, then we can combine at the end. So we're told the mean age of boys and girls. So for each category we do know the mean, so that could be highlighted in our formula triangle. And for both groups as well, we also know the total number of people. We know there's 18 boys and 27 girls. So we do know the total number of people in each group, and as well the total combined. So because we're wanting to initially anyway calculate the total of their ages, then we can work out the total mean using that. I'll highlight that in blue. Now you just cover up using your hand or finger whatever you want to work out. So if I cover up total ages, like so, I see that the total ages I can work out by doing mean age multiplied by number of people. So total age, mean age times number of people. One thing next to another in maths or algebra just means you multiply them together. So for the boys, we've got a mean age of 16.2 years. And there's 18 boys. So 16.2 the mean, times by the number of boys, 18. Let's see what that gives us. So 16.2 times 18 gives 291.6. Whereas for the girls, the mean age of the girls is 16.7, and there's 27 of them. So 16.7 multiplied by 27, let's see what this gives us. Times 27, 450.9. Then from these we can work out the total of ages. So based off these two values we just worked out, whoops, that arrow's facing the wrong way, jump. Total these up to get the total of all ages. Got 291.6 for the boys and 450.9 for the girls. So if you add these two numbers together, so we've got 291.6 plus 450.9, that gives us 742.5. So the total of all ages, 742.5. So we want to work out the mean age of all 45. So from this, we can now work out the overall mean. So the overall mean will be the total of all ages. So that's 742.5. Divided by the total number of people, which is 45. So the overall mean is the overall total of ages, which is 742.5, divided by the overall total number of people, which is 45. So final calculation, so we've got 742.5 there, we divide that by 45, press equals 16.5 exactly. So the overall mean age is 16.5 years, 16.5. For question 8, we have probability. So we've got some counters in a bag. The counters are blue or green or red or yellow. The table shows the probabilities that a counter taken at random from the bag will be blue or will be green. So 0.32 chance for blue and 0.20 chance for green. What we need to know and need to remember is that the sum of all the probabilities for any event will always add up to exactly 1. So these four numbers here, we don't know red and yellow yet. When we add them all together, that needs to give us 1. So far we've got 0.32 plus 0.20. So that gives us a total so far of 0.52. So 0.32 plus 0.20 gives us 0.52. Therefore, we can work out the sum of red and yellow by thinking that red and yellow must add to the 0.52 to give us 1. So to work out what the red and yellow must sum to, we can do 1 minus 0.52, and if we do that, we see that we get 0.48. So the red and the yellow combined must add up to give 0.48. So that's the first step. So based off that, we can then set up a table for figuring out what the probability for red and yellow are. So in terms of how to do this, we need to read this next line here. So the probability that a counter taken at random from the bag will be red is 5 times the probability that the counter will be yellow. That can only be the case if the number of red counters is 5 times the number of yellow. In other words, the ratio of red to yellow must be 5 to 1. So 5 lots of red for every 1 lot of yellow gives us a total of 6. However, we want this total to be worth 0.48. So to go from 6 up to 0.48, well, to go down actually, because 0.48 is smaller, what do we need to multiply by? Well, what we could do 0.48 divided by 6 to work out what we need to multiply it by. So 0.48 divided by 6 is 0.08. Essentially, you can think of this as pennies, 48 pence, 6p times 8 gets you to 48 pence. So multiply these other numbers by 8 as well. So 5 times 0.08 gives 0.40, and 1 times 0.08 is obviously just 0.08. So we can put these numbers into the table now, like so. Ultimately though, we're just wanting the probability for the yellow, because we've been asked what the number of yellow counters is. So that's what we're trying to answer. We can now use this probability to help us. So 0.08 as a proportion, a yellow. As a percentage, I think this is easier to think of it as. It must be that we've got 8% of the counters which are yellow. So 8%, which is the same as 0.08, are yellow counters. But how many counters are there in total? Well, obviously, there's 300. So what we need to do to work out the total number of yellow is to work out this percentage of the total 300. So 8% of 300 we can work out by simply taking 300 and multiplying by 8 shift a percent, and that gives us 24. So there must therefore have been 24 yellow counters, and that's our final answer for question 8. 24 yellow counters in that bag. Question 9, we have a diagram showing a prism. Now it says about the cross section of this prism has exactly one line of symmetry. So what do we mean by cross section of a prism? Well, the cross section is the slice of the shape that looks exactly the same as the back as it does the front. So it looks the same size throughout. So the cross section is just like, looks like the front of a house. So the cross section is all the way around this bit here. So I'm going to highlight this in red first of all. So that outline of red is the cross section. And as you can see, it's made up of a rectangle at the bottom and a triangle on the top. It's got one line of symmetry as well, which hopefully you can see is just straight down the middle. But if I colour code in the rectangle at the bottom and the triangle at the top like so, we can now think about what the area of a cross section is. Because the volume of a prism, and I'll mention this at the end, the volume is the area of this cross section I've coloured in multiplied by the length. So just taking this cross section and looking at it in a bit more detail, we've got this. So obviously that's 12 high because it says it's 10 across, but because it's got one line of symmetry, that 10 must be split equally into a 5 centimeters here and a 5 centimeters there. And what we can do to find out the area of this triangle on top is to find how high it is. We want to find the height here, h, I've labelled it. So just thinking of this triangle on the top now, just zooming in on the triangle only, this half of it, if that's the height, from the middle to the corner is 5 centimeters, this angle's 40, so it's a right-angled triangle. So to find h, we can use right-angled trigonometry, which you're probably more familiar with thinking of it as SOHCAHTOA. So now we need to just think about what side do we know, what side do we want to know. Well, clearly we want to work out the h, so we want to work out h, and that h is opposite to the angle we know. So we want to deal with a triangle that includes the opposite side. That's the opposite. So I'm going to tick O for opposite in all of these SOHCAHTOA triangles. The longest side is always opposite the right angle. So the longest side for hypotenuse is this one. I'm going to call that big H. We don't know that. We don't want to know it, so don't care. We therefore do know the 5. If this side isn't the opposite or hypotenuse, that must be the adjacent side, A. We do know the adjacent, so that's useful information. And we want to know O. So we're going to tick A and O. So the only triangle that includes what we know, A, and what we want to know, which is the opposite, is the TOA triangle. So we're going to be using and calculating based off this one. Now we want to work out the hypotenuse. Sorry, we don't. Want to work out H. Sorry, too many H's going on. I want to work out the opposite side. My apologies. The opposite side. So whatever we want to cover up, whatever we want to work out, sorry, is what we cover up. So because we want to work out the opposite, we cover up O, like so. And what's left tells you what to do. So O, we've got T and VA next to each other, and two things in algebra next to each other means multiplied. So we do tan times the adjacent. T stands for tan of the angle, so that's going to be tan of 40 in brackets multiplied by the adjacent, which is 5. And that'll tell us what H is. So on the calculator, we're just going to do tan of 40, close brackets, very important that, multiplied by 5. You get 4.195, 498,156. I'm going to write down all those numbers. That's not my final answer, so I don't want to round it quite yet. So I've got 4.195. What was the rest of it? 498,156. So that's H. So what we can now do is work out the area of this triangle. So the area of a triangle, so therefore area of the full triangle, not just that bit of it, but the full thing, is going to be as follows. So I'm just going to draw it on, so you don't think I'm talking about the right angled one, but the whole thing, which is this one here. Area of a triangle is half times the base. From all the way from one end to the other, the base is 10 times by the height, which is h, which we just worked out here. I'm going to multiply by that 4.195 number. So half times 10 times the answer we've just got. We may as well leave that stored. So it's half times the base, which is 10, multiplied by the height, which is our previously stored answer. So I'm just going to press ANS as a little easy cheat. Press equals, we get 20.977 and so on. So the area of that triangle at the top is 20.977 cm squared. So therefore, the area of a full cross-section is going to be the area of that triangle we just worked out. So 20.977 and so on and so on. Plus, as well, we need to work out the area of this bit here of the rectangle, which is obviously going to be fairly easy to work out because it's just length times width to work out the area of a rectangle. So this rectangle is 10 long, 12 high, so we're going to add on 10 times 12. So plus 10 times 12 gives us 140.977. And the final step to work out the volume of a prism is the area of the cross-section multiplied by the length of a prism. So we know the length of this prism is 20. So we're going to take this value here and multiply by 20. So therefore volume is going to be area of cross-section, 140.977, multiplied by the length of it, which is 20. And that'll be our final answer. So multiply this answer by 20. We get 2819.54 and so on. So 2819.54 ... But now we need to just check how accurate we need to give our answer. So we need our answer to 3 significant figures. So we just want to keep the 2, the 8, and maybe the 1, unless that 1 rounds up. Look at what the 1 is next to. It's next to a 9. 9 is 5 or higher, obviously. So that forces this one to round up to a 2. So we get 2820 cm cubed. Remember, units of volume are always cubed units of lengths. And that's our final answer given to the appropriate degree of accuracy. So that's all we need to do for question 9. Question 10. we're told a person's heart beats approximately 10 to the 5 times each day. Also as well, we're told a particular person lives for approximately 81 years. So work out an estimate for the number of times a person's heart beats in their lifetime. Give your answer in standard form, importantly, correct to 2 significant figures. So what we need to do here is to realise that these figures have already been rounded. It says approximately here and approximately there too. So estimate, you don't need to round them again. All we need to do is take these numbers and apply them appropriately. So 10 to the 5 times each day. So that's 10 to the 5 for one day. Then obviously in a year there's more than one day. So in any one calendar year, apart from leap years, there's 365 days. And so that's for one day, that's for the number of days in a year. So this step here is beats for 1 year. Obviously you don't need to write this in the exam, but I'm just explaining what this works out. But of course this person's living for just 1 year, living for 81 years. So then need to multiply that by 81 to get your figure. So if you do this on the calculator, you should hopefully get the figure, which I get right now. So 10 to the power 5 multiplied by 365 multiplied by 81. That gives us 29565 with 1, 2, 3, 4, 5 zeros after it. So first of all, what I'm going to explain is what this number actually is. Not that the exam needs you to prove that you know what this number is, but just in terms of reading numbers. How big is this number? It's so big, you won't normally see a number like this without it being written in words. So if you want to, you can just skip ahead a couple of minutes because this isn't needed for your marks, but just for understanding. You punctuate a number every third digit in from the decimal point, you punctuate with a comma, and this separates it into thousands, millions, billions, and trillions. 1, 2, 3, comma, another 1, 2, 3, then a comma, then another 1, 2, 3 back, and then a comma. So these are the hundreds and less, thousands, millions, and finally billions. So this is about 3 billion times in a lifetime your heart will beat. 2,956,500,000 times, approximately. But one thing to mention, in fact 2 things, this isn't in standard form and this isn't 2 significant figures. So I'll show you how to do this manually. Afterwards I'll explain how to do this automatically using the calculator. So if we want this to 2 significant figures, then what we're wanting is just to keep the first 2 non-zero digits from where the number starts. So we want to keep the 2 and the 9. So we might keep the 2 and the 9 as they are, so it'll look like 29, or the number next to the 9 might force the 9 to round up. Next to the 9 is a 5, remember 5 or more we round up, so this 9 has nowhere else to go, so we round up the whole 29, so the number's going to look like 30 now. I'll put it in black actually. So the number in standard form will look like 30, so it might be 3 or something like this. Now in standard form, the first number needs to be in between 1 and 10. So we need the decimal point immediately after the first number. So we want the decimal point to go here. Now clearly this is going to be a big number. So we want to times to the power of 10 a positive number of times. 30 isn't in standard form. So what we do, like I've done here, I put the decimal point here. Now we do need that 0. If you're thinking, well, can't I just call that 3? No, because you want it to 2 significant figures. So you have to have 1 and 2 significant figures written down. So the power of 10, what we do is we count how many digits are in between where the decimal needs to be there, compared to where the decimal place actually is in this big number. So if no decimal exists in a number, because for example it's a whole number, the decimal is invisible and lives at the end. So the decimal, you can imagine being here, followed by as many zeros as you want. So in between where the decimal needs to be and where the decimal actually is, we just count how many digits are in between, and how many digits are in between is our power of 10. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 digits in between Therefore, we've got 3.0 times 10 to the 9. And that's our final answer. However, if you're wondering, is there an easy way my calculator can do this? Well, yes, there actually is. So, do it the standard way on your calculator. Then what we can do is we can press Shift and then Menu. Now, we can get the number format to be to standard form by default if you want. So, press 3 for number format. SCI, because standard form is a scientific way of writing numbers, so press 2 for SCI. And then here you select how many significant figures you want the answer to be given to. We want 2 significant figures, so we're going to type 2, then we're going to press equals, and then you can see the calculator will generate the answer we've got manually, 3.0 times 10 to the 9. Don't panic if you're thinking, well, how do I get back into normal mode now? Don't worry, just press Shift, Menu, then go to number format. You want it back to normal, so 3 is NORM, norm for normal, and for some reason, option 2 I think is better. So 1 or 2 is fine, press normal option 2, and then you're back to normal. So that's 10A, 3.0 times 10 to the 9. For 10B, we're told that 2 times 10 to the 12 red blood cells altogether have a total mass of 90 grams. Work out the average mass of one red blood cell, again give your answer in standard form. So 2 times 10 to the 12 cells, they have a mass of 90 grams. But we want to work out the average mass of just one red blood cell, so we want just one cell. So what can we divide 2 times 10 to the 12 by to get down to 1? Well, you need to know and remember almost automatically that any number divided by itself always gives you 1. 2 divided by 2 is 1, 17 divided by 17 is 1, and so on. So we can divide this number by itself. We can divide the left-hand side by 2 times 10 to the 12. However, with equations, what you do to one side to keep the balance correct, you need to do to the other. So to work out the mass of one cell, I also need to do 90 and then divide that by 2 times 10 to the 12. And when I do that, that will tell us what the average mass of one red blood cell is. So this is what we do. So we're going to do 90 divided by, now put this all in brackets, 2 times 10 to the power 12. Close brackets and press equals. You now have, already in standard form, so we don't need to get our calculator to change the format, 4.5 times 10 to the power minus 11. So that, according to the question, is the average mass of one red blood cell. They don't weigh much, and, well, as you'd expect. Question 11. So this is one about transformations. So we've got a diagram showing triangle P on a grid, as you can see. Now it's going to be rotated 180 degrees about 0, 0 to give triangle Q. So 0, 0 is going to be there, so that's going to be our centre of rotation. We also need some tracing paper in a moment. So first of all, we're going to label our centre of rotation or mark it. Next, we're going to use tracing paper to trace over shape P. As well, what we're going to do with the tracing paper is we're going to hold it in place with something sharp over the centre of rotation. So here I've just shown you a compass. It doesn't need to be a compass needle, it could be your pen or pencil. So now with the tracing paper, we're going to shade over P, like so. Then we get the tracing paper, put the traced triangle right on top of triangle P, so you can't see it like, you can see how I've got mine here. That white triangle of traced exactly covers for what shape of traced over. You hold the centre of rotation, stab the actual tracing paper down over the centre of rotation with something sharp. Then we're going to turn it now. So hold the paper at one edge, and then you can spin the paper around, which I think is easier than actually turning the tracing paper. Whichever way you do it, we're going to do half a turn from here to down here somewhere. So we get the tracing paper, and then we're going to just do a quarter of a turn like this, go again for another quarter term to make a full half, we get that the triangle P should be down here. So what we do next is we go over triangle P and label it on the grid as triangle Q. So that's triangle Q. Next, we're told about a translation. So triangle Q is translated by 5 minus 2 to give triangle R. Well, 5 minus 2 means each point on Q means 5 to the right and 2 units down. So this point here is going to go 1, 2, 3, 4, 5, then 2 down. So the tip of that triangle will end up here. In fact, all points are going to move 5 to the right and 2 down, like so. This point moves here, the right angle moves there, and so on. So we just take these points, dot, 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 join them up and label to give triangle R, like so. So we had from P, then to Q, then from Q to R. So as a single transformation, what would it be that would map P onto R? Well, first of all, we need to think there's 4 different types of transformation. It's not an enlargement because P hasn't got any bigger or smaller. P and R are the same size and shape, so it's not an enlargement. Is it a reflection? Well, there's no way you could put a mirror to P and make it look like R, so it's definitely not a reflection. It's not a translation either because P and R are different ways up, so they're the opposite way up to each other, so it can't be a translation. A translation is when they look the same way up, for example Q and R. So the only other thing to think about is it's got to be a rotation. And because R is P flipped upside down on its head, it's a 180-degree rotation. So that's the first thing to say. For single transformation, it's going to be a rotation of 180 degrees. Now what we need to think about is where the centre of rotation is. And one way of doing this with triangles is we do straight lines from each point on the original shape to the corresponding point on the rotated shape. So we're going to do straight lines connecting each of these points. So connecting the right angles together, then connecting the sharp points together, and finally connecting that point to this point gives that. And what you should find with any triangle when you do this is the lines all cross at a single point, as you can see here. And that point is the centre of rotation. So it's halfway in between 2 and 3 units, so it's 2.5 along and 1 down. So the coordinates of this are 2.5 minus 1. So then we just say a rotation of 180 degrees with the centre of rotation 2.5 minus 1. If you had time at the exam to check your answer, then what you could do is actually just use tracing paper and see if that's right. So if we get rid of these lines for a moment, and then put this centre of rotation back in, like so, and then if we were to trace around P again, or get the original tracing paper that we traced P around the first time, like so, and then turned it 180 degrees, then you would indeed see that it's right because it maps directly on top of R. So that's the way you could double check it, if you had time of course, in an exam situation. So part B, what it's saying here is under the transformation that maps triangle P onto R, the point A is invariant. So first of all, what on earth is that word invariant? What does it mean? It's a fancy word, but all it actually means is that a shape, point A this is, just means it doesn't move. That's all it means. Invariant means it does not vary, it doesn't change, it doesn't move. So when we rotated this shape here, imagine the tracing paper as one whole entity. The whole tracing paper is moving. The triangle's moving, the top of the paper's moving, that end of the paper's moving, but only one point on this tracing paper isn't moving. And the point that doesn't move is the centre of rotation itself, because everything moves around that point, but not that point itself. So the invariant point is the centre of rotation from part A. This coordinate here is the invariant point. So A is 2.5 minus 1. Question 12. We need to express x over x plus 2 plus 2x over x minus 4 as a fraction in its simplest form. So what we need here is a common denominator. So what we can do is cross multiply each fraction by the opposite one's denominator. So take x and x plus 2, and then we can multiply x over x plus 2 by x minus 4. So we're going to times both top and bottom by x minus 4, because obviously with fractions, what you do to one side, you do to the other. So I'm going to times that by x minus 4. I'm going to times this here, which I'm going to put in brackets now, by x minus 4. And to that, we're going to add 2x over x minus 4. And what we're going to do here, we're going to multiply both top and bottom of this fraction by the opposite one's denominator. So we're going to multiply both top and bottom by x plus 2. Now, the trick here is, because you've got these under a common denominator, but it says simplest form, there's a good chance it's going to simplify. So we can put the numerators together over this one common denominator of x plus 2 brackets x minus 4, but it'd be a wasted step now to expand the denominator. Leave the denominator factorized as x plus 2 x minus 4, and instead write down x brackets x minus 4 and 2x brackets x plus 2 on top of that fraction. So now what we're trying to do is we're going to see if we can expand and simplify the top, then factorize, and it might well match the bottom. This is a commonly employed exam question type that Edexcel and other exam boards do, where they want you to have an algebraic fraction, have both top and bottom factorized, and then often you can cancel one of the factors on the top and the bottom. So that's what we're aiming for, seeing if we can do that. So expanding out the top, x times x, and then x times minus 4. X times x gives x squared, x times minus 4 gives us minus 4x. The second bracket, 2x multiplied by x gives us plus 2x squared, and then 2x multiplied by 2 gives us 4x. Then the bottom we can leave as x plus 2 x minus 4. Finally, see if we can simplify the top of a fraction. And of course we can. One thing we should notice is we've got a 4x here and a minus 4x there, which will cancel. So all we're going to be left with is these x squareds. So 1x squared plus another 2x squared gives us a total of 3x squared on the top. So actually, that doesn't cancel with anything on the bottom, so we just have to leave it as it is. So the fully simplified fraction is 3x squared all over x plus 2 brackets x minus 4. Let's have a look at part B next. So part B, we're asked to expand and simplify 3 sets of brackets. So x minus 3, 2x plus 3, 4x plus 5. So my suggestion here is to work from back to front. Expand together the last 2 brackets here, and then finally the answer to that times out with x minus 3. So I'm just focusing on these last 2 brackets here for now. So my preferred way of expanding 2 by 2 brackets is using the box method. Whatever your teacher tells you, whatever method you're comfortable with, but the method I'm going to show you is using this box here. So we can do the boxes in any order you want to, but importantly, we just multiply what above the box by what's to the side of it. So first of all, I'm going to do this box. So 2x times 4x. Well, 2 times 4 is 8. X times x is x squared. This box next, 4x times 3. So that's going to be 12x's. Down here, 2x times 5 is going to be 10x. And this final one, 3 times 5, is 15. So if I fully simplify this one now and group stuff together. I've got 8x squareds. 10x plus another 12x's is 22x's. And finally, I've got this 15 as well. So I've got 8x squared plus 22x plus 15. I then take this answer, which is that, and I now multiply all of this, which of course is this, by the x minus 3 at the front. So the final step now is to take this 8x squared plus 22x plus 15 and times by the x minus 3, and I'm going to do it in a grid as well, like I've done before. So we take this here, write it along the top. So I need an extra column now, because this is 3 terms, and 2 rows for the 2 terms, the x and the minus 3. So take your time, it's no harder than the first set, simplify at the end, and we're done. So 8x squared times x gives 8x cubed. 22x times that x gives 22x squared. X times 15 at the end gives 15x. 8x squared times 3 would be 24x squared, but because I'm timesing by minus 3, that needs to be minus 24x squared. Then 22x times 3 again would give 66x, but because it's a minus 3, this is minus 66x. Finally, 15 times 3 would be 45, but again, you've guessed it, because that's a minus 3, that makes this minus 45. Finally, just pull all this together and simplify. So I've got one lot of x cubes here, so that's 8x cubes altogether in that pile. So I've got 8x cubed. Then the x squareds, well, I've got 22 here, then I need to minus 24 there. So 22 minus 24, if in doubt, use your calculator. Get minus 2. So then I'd have minus 2 x squareds. Now we can look at the normal x's. So I've got 15 here, but I'm taking away 66 there. So again, on the calculator if you want, what's 15 take away 66? That's minus 51. So I'd have minus 51 x's, and finally that minus 45 needs to live on the end as well. So just underline that, and we're good. That's the fully expanded out set of 3 brackets. 8x cubed minus 2x squared minus 51x minus 45. Number 13 is about representing inequalities on a coordinate grid. So on the grid, we need to show these 4 inequalities and then shade the region as well where all of these 4 inequalities are satisfied, and then label that region R. Before we get started though, I just want to give you 3 pointers for how to do these questions generally. So first of all, what I'd say is to imagine the inequality symbols here as just a simple equals, and then draw on those lines on the coordinate grid. So for example, I'm going to suggest we think of this one, just picking this one randomly, as y equals x plus 3, and plotting that on the grid like you would have done in year 7, 8, 9. So think of them as equal signs and draw on those in the normal way. The second 2 things to mention, I'm going to mention together. So inequalities with a line underneath a symbol, we represent those with full lines, and similar to that, inequality symbols without the lines underneath, for example that one or that one, need to be represented with dashed lines. So by full lines, I just mean a line without any dashes. So a full line is something like this, and by dashed line, I mean something like that. Now the way I remember it is to do an inequality symbol with a line underneath takes more ink from your pen, more lead from the pencil, more ink from the printer, whatever. This takes more ink than without doing dashes. Also, a full line takes more ink as well. So more ink is a full line and a line underneath the symbol. This takes less ink without doing the line underneath, in the same way that a dashed line would also take less ink from your pencil, because you're giving your pen or pencil a break in between by leaving gaps. It's a silly thing to say, but that's how I always remember it anyway. So, returning and using these points here, what we're going to do first of all is just think of these colour-coded. So, purple, x greater than or equal to 0, then red, blue, green. And like I said, I'm going to replace these symbols of equals is, just so it makes a bit more sense. So the first one I need to draw on is where x is equal to 0. If you're not sure how to do that, I'm going to give you a few pointers if it's like an x equals a number or y equals a number. Just pick any coordinate you want where x is equal to 0. So let's pick, for example, 0 and 5. That would be this point here. Or maybe you want to pick 0, 3. Or when x is 0 and y is minus 1. Eventually you should realise, so an x equals line is always vertical and cuts the x-axis where x needs to be equal. So x equals 0 is a vertical line cutting x where the x-axis says 0. So the first purple one we can draw on, like so. Then the line x equals 2, same idea, it's an x equals line, so it's going to be a vertical line, this time cutting the x-axis where x is equal to 2. Before we do that though, we need to just think about actually what we want x to be. Now here, this means x is actually greater than or equal to 0. So after you draw the line, return and consider the inequality. I want x to be greater than 0. So x needs to be on the big side of 0. In other words, x needs to be over here somewhere. We don't want x down here. So I'm just going to blot out the side I don't want with some crosses, like so. So the crosses means this is not going to be our region. Now we've done that, let's do the line x equals 2. So a vertical line going through the x-axis at 2, like so. This time, now we can consider the inequality. This time we want x to be on the smaller side of 2. This hungry crocodile would rather eat 2 than the x. So x needs to be smaller than 2, not bigger. So I want x to be over here somewhere, not on the big side. So again, I can put crosses over here. This is where I don't want x to be. So something like this. Now the blue line, y equals x plus 3. That's going to have a gradient of 1, because it's just y equals 1x. And it's going to cut the y-axis when y is equal to 3. This is the y-intercept. So this blue line is going to look something like this. Then return and consider the inequality. Y is smaller than x plus 3. Now remember, y is the up and down direction. If we want y to be on a small side of something, we want y to be underneath. We want y down here somewhere. We don't want y on the big side. So again, in a neater way, we cross off the top and say we want to look at the bottom bit here where y is smaller, like it needs to be. You'd have something like this. Now finally, this one isn't in the form y equals. So what we need to do is rearrange it. So if we subtract 2x's from both sides, we get that 3y equals minus 2x plus 6. Then if we divide everything by 3, we get y equals minus 2/3 of an x plus 6 divided by 3, which is 2. So rearrange it into y equals first, like so, and then plot this line. So it's going to crop the y-axis at 2, and for every 3 units along, we're going to go down by 2. So it's got a gradient of minus 2/3. So this is a bit harder to plot, but the line y equals minus 2/3 of an x plus 2, or the line 2x plus 3 equals 6, looks like this. That's where you need to draw the line. That's the hardest bit of this whole question. Now consider the inequality. Okay, so we rearranged it here, but actually what it would be is y, using the same symbol, greater than minus 2/3 of an x plus 2. That's the actual inequality as it would be. So we want y to be on the high side of what we're comparing it to. Y is higher above the line, so we don't want anything below our line. So we cross it all off here, something like this if you did it neatly. Now we've drawn the 4 lines, and we've crossed off where we don't want the region. Therefore you should see this trapezium shape here, which is enclosed by these 4 different lines. That must be the region which is allowed. So what we need to do here is shade in this middle region. It does say show by shading, so I'm going to shade this in my blue colour. You just use your pencil and shade it in. And we're almost done, but what it does say as well, which is almost hidden by what I've written, You need to label it R. So with a nice big clear R, smack an R in your region, like so. And that's question 13A done. Oh, look at my R. It's not spun right for A round. That's going to annoy me. Just can't get the staff, can you? Sorry, everyone. There. Says me up for trying to be too fancy and failing spectacularly. But there. That's region R. Forgive me. Part B, we've got this diagram here showing region S, which satisfies the below inequalities. Y less than or equal to 4x, y bigger than or equal to half of an x plus y less than or equal to 6. Jeffrey says that the point with coordinates 2, 4 does not satisfy all of the inequalities because it does not lie in the shaded region. Is he correct? Give a reason. Well, 2, 4 is that point there. And so it's actually on the line. Okay, it's on the line, it's not outside the region. The key is with these symbols. These symbols mean it is allowed to be equal to the line. It's not strictly less than or more than. Because we've got this line here, it's essentially saying we're allowed to be equal to it. Literally, this is where the symbol comes from, because look a bit like equals is. So being on the line, being equal to it is fine. So is he correct? Actually is not. So no, he's incorrect, and this is just an example of wording which would be okay to use. He's incorrect because 2, 4 lies on the boundary of a region, but the boundary itself is included in the region. It's a solid line. If this was a dashed line, then Jeffrey would be correct. But because it's a solid line, unfortunately for him, he's incorrect. Question 14, we have a circle theorem question. So we need to find the size of angle ABD, it says. So whereabouts is angle ABD? Well, you always go on the middle letter. So it's the angle at B here as you move from A to B to D. So I'm just going to label on the actual angle we're trying to find in a red colour. So the angle we're wanting is this one in the corner. So where can we start here? Well, what you need to notice is B to D to E to F. They all lie on the circumference of a circle. So I've highlighted them in blue, this quadrilateral. If all points of a quadrilateral lie on the circumference of a circle, this is called a cyclic quadrilateral. And one of the circle theorems which we're going to use now is that the opposite corners of a cyclic quadrilateral will always add up to 180 degrees. If this one here is 100, that one there needs to add to 100 to give us 180. So if that's 100, this one must be 80, such that 100 plus the 80 gives us 180 degrees like the circle theorem says it must. So because that's 100, this one must be 80. Then you say to the examiner, to get your marks, just say give a reason, angle DBF, is this one here, is 80 degrees, put your reason in, opposite angles in a cyclic quadrilateral add up to 180 degrees. That's your hardest one probably, or one of them. The next one's a bit simpler. Look at this here. This makes a triangle. So 80 plus 40 plus something needs to add up to 180 degrees. 80 add 40 is 120. Therefore, this angle at F must be 60 degrees because angles in a triangle add up to 180. So as obvious as that might be to you, you need to explain it to the examiner to give them all the possibility you can of giving you more marks. So then we say the angle BFD is 60 degrees because angles in a triangle obviously add up to 180. The final one is again a circle theorem question. From A to C is a tangent, and if we just focus in on this triangle shape at the top, in fact I'll put this triangle back in a moment, but I'm just looking at the top triangle here, then that angle here will be the same as this one here, and that's called the angle in the alternate segment. So if you've got a triangle touching at one point a tangent, the angle in the triangle that isn't attached to the side that the tangent's touching at all, for example, this tangent here, this angle is making contact with this side. The angle which is right away from this one is the opposite one here, which is 60 degrees. So because that's 60, that must be 62. So we put therefore that angle ABD is 60 degrees, and the reason for that is that angles in the alternate segment are equal. So that's your final answer, and that's your working to give to the examiner to make sure you pick up maximum marks. Question 15. We have to prove algebraically that 0.73 recurring can be written as 11/15. So I'm going to just put a grid on the board here just to make it clearer for myself and clearer for you. Okay, so here we are. So why I'm doing this is that we can now call this decimal x, and then we're going to use a strategy which will become very clear. So all we do is to say let x equal 0.73 recurring. That dot above a 3 means that 3 is going to be going on forever. And so I'm going to write x here, and then what I'm going to do is I'm going to put a decimal here, a decimal here, and a decimal there. In fact, to make myself enough space, what I might actually do is just put them here. But you'll see what I'm going to do in a moment. So, 0.73 recurring, I'm just going to write down what this is. So it means 0.7333, and those 3's are going to go on forever. So this last 3, I'm just going to put dot, 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 just so it's clear to the examiner that these 3's aren't just going to stop there. Next, what we're going to do, we're going to multiply by 10s until we get rows which have the digits lining up. You'll see what I mean in a moment. So I'm going to multiply x by 10 to get 10x. And if I do that, what's going to happen here? These digits are all going to shift one digit to the left. So in other words, the decimal, you can think about it as moving to the right. So 0.7333 is going to become, after you multiply it by 10, 7.333333. Now if you notice, these numbers do line up because these 3's here forever on the right will cancel, will cancel, will cancel if you to do one line take away the other. And that's the trick. You keep going until they line up, which they do. If they didn't, we times by 10 again to get 100 x's. But when they line up, you just do one line, subtract the other. So what we're going to do now is 10x's subtract 1x. And that will obviously leave us with 9x. So 9x, we think about doing the subtraction as you would like an old school subtraction. So 3 take away 3 obviously cancels. 3 take 3 cancels, and so on and so on and so on, until you get to here though. 7.3 take away 0.7. That doesn't cancel. Make sure the decimals line up. This is a calculator paper, so you could even just do 7.3 take away 0.7 on your calculator if you want to. But to be a Puritan, I'm going to do it the old school way. 3 take 7 you can't do, so borrow 1 from the 7 to make it a 6. The 1 we borrow goes here to make the 3 13. 13 take 7 is 6. 6 take 0 is 6. So therefore, 9x must equal 6.6. And so x must equal 6.6 over 9, which obviously isn't that. What I'd suggest we do is we get rid of a decimal. My suggestion here would be to multiply both top and bottom by 10. Okay? So times by 10, times by 10. So x equals 6.6 over 9, which is the same as 66 over 90. Then on a calculator, because it is a calculator paper, that will simplify down. Essentially, both top and bottom can be divided by 6. If you want to be explicit, you could say this to the examiner. Look, examiner, I'm dividing both sides by 6 because I know what I'm doing. Which of course you do because you've revised. So 66 divided by 6 is 11, and 90 divided by 6 is 15 as required. So therefore, we're done. Simple as 11/15. With practice, these questions actually become fairly simple. If you don't think they're simple yet, practice, practice, practice. Question 16, we have a speed time graph for a car, and we're asked for part A to work out an estimate for the distance the car travelled in the first 30 seconds. What you need to remember for GCSE maths, and I still believe GCSE physics, is that the area underneath the curve for a speed time graph or a velocity time graph will tell you the total distance travelled exactly. So because we're trying to work out an estimate, we need to estimate the distance underneath this curve up to 30 seconds. We're not wanting the full 150 seconds, just the distance covered in the first 30 seconds. So like I've said, the key thing you need to know and need to remember is this. The area under the speed time graph is distance travelled. We only need an estimate though of that distance, so we don't need to work out the exact curved area between 0, 9 and 30. We can estimate the shape of it. So to me, and I imagine to you as well, from 0 up to that 0.9 down to 30 can be approximated pretty well by a triangle. It doesn't need to be exact because again this word estimate lets us off the hook. It needs to be about correct. That's pretty close. It's not including this bit, but we'll come to that in part B. So like it says, we need to work out the area of this triangle. So the area of a triangle, we need to know its base and its height. So the base is 30, as you can see, and it goes up to 9. Then the area of a triangle is half times base times height. So in our case, that's going to be a half times 30 times 9, which if you do that on your calculator, you should find that it's 135. Therefore, because it's not unitless, we're working out the distance travelled. The unit of distance mentioned in the speed is meters per second, but because meters is mentioned here, our units of distance will pop out to be meters. So therefore, the distance travelled is approximately 135 meters. So, next up, part B asks us if the answer to part A we just got, 135 meters, is that an underestimate or an overestimate of the actual distance the car travelled in the 30 seconds? Give a reason for your answer. Well, the exact area under the curve tells you the exact distance travelled. We did an approximate distance, therefore got an approximate area, therefore an approximate distance travelled. So it's an approximate because, as you can see, hopefully, there's a tiny bit under the curve which we didn't include in our triangle calculation. This tiny bit here, which I'm going to colour in purple, you can see wasn't included. Now this purple bit is still under the curve, so should have been included, but we worked out the area of just the triangle, so essentially we ignored this bit underneath the curve, so we didn't quite get the entire area. Because we didn't get the entire area, we didn't do an estimate of the entire distance, so we've underestimated it because we've underestimated the true area. So the wording you might want to include could be something like this. It's an underestimate of the actual distance because there is a small area between the triangle and the curve, which we did in purple, that was not included in our calculation. Then moving on to part C. For part C, I've highlighted this point here. This is the point where Julian used the graph to answer this question. So he was asked to work out an estimate for the acceleration of a car at time 60 seconds, which is at this point here. So that's at a speed of 13 meters per second when the time's 60. So his working goes, acceleration is speed divided by time, which is 13 here, divided by 60, and that gives you 0.216 recurring meters per second squared. It then says Julian's method does not give a good estimate of the acceleration at time 60 seconds, and it asks us to explain why. Well, the first clue really is in the wording here. The acceleration should always say change in speed or a change in velocity divided by the time taken. So because there's no change, he's not worked it out correctly. Another thing that could be said is the time is used is the total time of the journey up to the point of 60 seconds. So he's worked out the total average acceleration throughout the 60 seconds. So he's worked out an average acceleration, not the exact acceleration at the instant of 60 seconds. So again, the wording you could use could be something like this. He's calculated the average acceleration over the first 60 seconds instead of the acceleration at the time of 60 seconds. So what should he have done? What would have been right? Because it's a curve and not a straight line, you needed to take this point at 13 and 60, and then you needed to work out the gradient of the tangent at that point. So here's what he should have done. He should have worked out the gradient of a tangent at the time t equals 60 seconds. A tangent is a straight line that just scrapes the curve at that particular point. So a straight line that just touches at the instant of 60 seconds would look something like this. He then should have picked 2 points on this line, maybe this one and maybe that one, then worked out the change in y divided by the change in x of those 2 points. That would have given him the correct estimate of the acceleration at this particular point in time. Question 17, we have a histogram here giving information about the distances 80 competitors jumped in a long jump competition. We need to calculate an estimate of the mean distance. So how could this question have been asked to you in a different way? Estimating the mean distance is often asked from group frequency tables. So a question you might see is like this, where you have a grouped frequency table, then frequencies, and then you need to do midpoint, and then midpoint times frequency. I'm sure you've seen those before. So that's what you might have normally seen, but here you've got a histogram. So your task essentially is to take this histogram and convert it into one of these, which is more familiar. We need to get this information into this table if we can. And that's where these class intervals come from. So this here is representing the people that jumped somewhere in between 6.4 meters and 7.2. So this interval goes from 6.4 up to 7.2. Likewise for the other ones, from 7.2 to 7.6 is a second bar, so that's our second row. The third bar is the people that jumped in between 7.6 and 8 meters, so that's our third row. And the fourth and final row, for the fourth and final bar, is the people that jumped in between 8 meters and 8.2 meters. We now need to work out the frequencies for these bars. And we're told here about frequency density. So what formula links frequency and frequency density? You need to remember this one. So frequency density equals frequency divided by class width, which you can put into one of these formula triangles like I have here. So frequency density equals frequency divided by class width. Or you can remember it by this very stupid mnemonic, which is very immature, but it works for me. It says more about me than anything else. Fat dads feast on chicken wings. That's a very silly way, but it might help you to remember it. So FD is F divided by CW. We want to work out the frequency, so what we do is we cover up F with our thumb or our hand, and what's left tells us what to do. So if we see here, we cover up with a hand F, we've got FD and CW next to each other, which means we take the frequency density and multiply it by the class width, in the same way that 2x would mean 2 multiplied by x. Two things next to each other means we multiply them. So we can read off this graph here, in fact. So for the first bar, we can see here that this has a frequency density of 10. So this one goes for 10. So the frequency for this one will be the frequency density, 10, times by the class width. From 6.4 to 7.2 is a difference of 0.8. So this one we're going to do 10 multiplied by 0.8, or 0.8 times 10, which gives us 8. The next one goes from 7.2 to 7.6, so this one has a width of 0.4. This frequency density is up at 50, so this one's going to be 0.4 times 50, which gives 20. The next one, again, is a width of 0.4, and its height is 100. So this one will be 0.4 times 100, which gives you 40. And the final one, from 8 to 8.2, that's got a width of 0.2, because that's 8.2 there, and a frequency density of 60. So 0.2 multiplied by 60 gives us 12. Now what we need to do is to work out the midpoints of these intervals. So midpoints for each of these. So halfway between 6.4 and 7.2, that's going to be 6.8. Halfway in between 7.2 and 7.6, that's going to be 7.4. Halfway in between these two numbers is 7.8. And halfway between these two is going to be 8.1. Then what we do is we multiply each frequency by its corresponding midpoint, and a fourth and final row here gets something that looks like this. So frequency times midpoints, actually just complete the calculations for these 4 rows and end up with something a bit like this. So we're nearly home and dry now. The final thing to do is to total up this column and also to total up total frequency. Or you could just read the question carefully, which I have not done. It does say, gives information that the distances 80 competitors ran. So if you do total up all of these, you should find it comes to 80. If you had time in the exam, I'd suggest you do that anyway, because this will show you if you've done the frequencies right using the frequency density formula. So 8 plus 20 plus 40 plus 12. I hope that gives me 80. Does it? Look, yes it does. Therefore, phew, I'm probably on the right tracks. Now we total up this column too. So we've got 54.4, whoops, plus 148, plus 312, plus 97.2. We press equals, then SROD, we get 611.6. So therefore our estimate for the mean is going to be about 611.6 divided by the total frequency of 80. So let's see what this gives us. So that total there divided by 80 gives us that. So we can round it if you want to 3 significant figures. We can call that 7.65 meters if you so wish. So mean 7.65 meters. And that's our estimate. So it's about unpicking the question and making it from something that looks quite confusing into something a bit more familiar. That's the lesson to be learnt there for that one. Number 18, we've got a cube. So we're told that AH is 11.3 centimeters correct to the nearest millimeter. So what do we need to do here? Well, first of all, we can think about what from A to H actually is. So from A to H is from one corner to the opposite corner. So we might want to label that in so we've got a feel for what we're trying to actually end up with. So that's the line we're trying to work with, and that's 11.3. So we can label this on first of all. So this AH we can imagine as being part of a triangle as we drop down from A straight down to F, then from F across to H. So this here, this solid line of these 2 dotted lines make a triangle. So now we can think about the length of an edge of these sides. So the length of each edge of the cube we could just call, for example, x. So x long, x high, and x wide. So now if I just think about this base, or this triangle on the base of a cube, and then just picture it, if that side's x, this side x, that's is obviously going to be a right angle. We could work out this dotted side here by considering it as a right-angled triangle problem. So x, x, I'm trying to work out this dotted side here, that diagonal from F to H. This is going to be Pythagoras we can use. So the hypotenuse squared, the question mark squared, must be this side squared plus this side squared. So by Pythagoras, what we'd have is question mark squared equals x squared plus x squared. X squared plus x squared simplifies to just 2x squared. So therefore this hypotenuse, which I've just called question mark, you could have called it a different letter like y, this must be equal to the square root of 2x squared. So now we know what from what F to H is, we can add this to the diagram. So I now know in terms of an unknown x, this must be root 2x squared. We can therefore think about using Pythagoras on this red triangle now as well, which I'm going to colour code in green. So we know its hypotenuse, AH, is 11.3 to the nearest millimetre at least. The base, in terms of a side of a cube x, is root of 2x squared, and this side here is x. So thinking about this green triangle and putting it into our diagram of our own now, we've got this. So the question originally says to the nearest millimetre. So to the nearest millimetre, to one decimal place essentially, we've got this. So by Pythagoras again, x squared plus the square root of 2x squared all squared equals 11.3 squared. But actually, we're not just thinking about one decimal place here. We're wanting to be thinking about the lower bound. So the lower bound for the length of each side would give the lowest bound as well for AH. So if x was as small as possible, so would AH be as small as possible. But if AH is 11.3 to one decimal place, what's the absolute smallest it could have been, so that it would have just about still have rounded up to 11.3? The lower bound of AH, therefore, actually must be 11.25. So considering lower bounds, we'd get rid of 11.3 and instead consider it as 11.25. We can now apply Pythagoras to this triangle, thinking of it in terms of lower bounds. So using the smallest possible edges only, now what we're going to have is this to solve. And if you can solve this for x, we've solved it for the lower bound. So we've got x squared here. Now if you square a square root, one undoes the other. So essentially the squaring cancels the square root, if you like. So we're just going to be left with 2x squared. And that's going to equal 11.25 squared. If you want to, you can calculate what 11.25 squared is at this point. You don't have to, but if you do, that's no harm. So that gives us 126.5625. This is obviously 3 lots of x squared, so 3x squared is 126.5625. We can divide both sides by 3 now to get what 1x squared is. So divide by 3 and divide by 3 there. That tells us that x squared equals, I can't do that in my head. Oh, got these numbers mixed up as well. So 5625 that should say. So my bad. So I just need to divide by 3 once I've corrected my little error. There we go, dividing it by 3 gives us this thing here, 42.1875. Final step, we just square root both sides. So square root the x squared and square root that. So therefore the lower bound x is going to be the square root of 42.1875. So take this answer here, square root my answer, and I get 15 root 3 over 4. This is a surd. It's best to give this as a rounded decimal, I'd say. So if in doubt, give it to 3 significant figures, I would suggest. So here, I'm going to say we go for 6.50, because that 5 next to the 9 makes that 49 round up to 50. So we have 6.50 centimetres. And then we're done. Question 19, we've got 2 similar hexagons. So we've got A, B, C, D, E, F, which is a regular hexagon with sides of length x. So enlarged from that by scale factor p is this much bigger hexagon in grey, F, G, H, I, J, K. We need to show that the shaded region is given by this horrible looking thing here, 3 root 3 over 2, brackets, p squared minus 1, close brackets, x squared. This is where the questions get pretty nasty towards the end of the paper, so let's unpick it together. First of all, it's a regular hexagon with sides of length x. So let's focus in on this smaller smaller hexagon A, B, C, D, E, F. So I'm going to highlight this in a blue, and now we need to remember something really important here. So if you've got a hexagon, you need to think about how a hexagon can be made or considered by. So any hexagon, regular hexagon, you can think of that as consisting of 6 congruent equilateral triangles stuck together in the middle. What I mean is this. So imagine slice from the middle down to each vertex, each corner, like this, you'd have 6 congruent equilateral triangles, each with 60 degrees at the centre. The full 360 divided by 6 gives 60, 60, 60, 60. And we've been told that these have side lengths x, so we can label on x, x, and x. So right now I just want to consider one of these equilateral triangles, this one at the bottom. Like I say, it's got an angle of 60. All the angles, in fact, will be 60. We can now work out the area of this yellow triangle. So just thinking about these two sides, yes, this one is x as well. The area of a triangle generally is half AB sine C, where you've got two sides either side of the angle you know, multiplied by the sine of the angle you do know. That's the area of any triangle. So for this one, the area of it is half times x times sine 60. I know that x times x is going to give me x squared, so I can work out what half of sine 60 is. So if I just do here 1/2 times by sine 60, that gives me root 3 over 4. So this is going to be root 3 over 4 x squared. So that's the area of one of the yellow triangles. But of course, this smaller hexagon isn't just one yellow triangle, it's all 6. So I need to imagine another 5 joining in here, like so. So the area of a full hexagon would be 6 times root 3 over 4x squared. And if you do that and do 6 times root 3 over 4, you'd get 3 root 3 over 2 x squared. So the area of a full smaller hexagon is 3 root 3 over 2 x squared. Now we need to consider this bigger one here, FGHIJK. We're told this bigger one, you get it from enlarging the smaller one by scale factor p. So what does it mean to enlarge something scale factor p? Well, essentially what it means is, for each unit of length on the original shape, you multiply that unit of length by the scale factor to get the new size. So for example, if the scale factor was 2, you'd times the sides by 2. You'd double everything. If the scale factor was 10, if p were 10, you'd multiply all the sides by 10. So if the scale factor is p, you times each unit by p. So that's what it means. It means that the length of a small hexagon, the original, compared to the length of the bigger one, is 1 dot dot p. For every one original unit, we multiply it by the scale factor to get the length in the new shape. 1 times p gives p. We now need to consider, from length ratios of similar shapes, the area ratios and not the volume ratios here, but if you know the length ratio is 1 dot dot p, then the ratio of areas of the small to the big will be 1 dot dot p squared. So this is the area ratio we're going to use now. So we've got the area of the, obviously, smaller hexagon to be this. So using what we've got here, we can say that, therefore, area of large hexagon that's going to be this thing here multiplied by p squared. So it's going to be 3 root 3 over 2 times by p squared. So instead of just being that times x squared, it's now p squared x squared. So we've got the two main bits now. We know the area of the yellow one, which is this, and the area of the larger one, which is that. So what we can do now, we can consider the shaded area as just being the big hexagon take away the small one. So therefore now, shaded area that's just going to be the area of the big hexagon, which I'm terrible at drawing a hexagon. The big one is FGHIJK, minus the area of the smaller hexagon, which is ABCDEF. So if we do this now based on what we know, then the smaller hexagon we worked out to be 3 root 3 over 2x squared. So we're minusing 3 root 3 over 2x squared. But the area of the larger one we worked out to be 3 root 3 over 2 p squared x squared. Now, we're almost there, but just return to what we want to show it to be. So we want some of it factorised out, but then we want the x squared to be hanging at the end. So we're trying to factorise out all of this away from the x squared. So this is what we're aiming for. So I'm going to copy this down and just aim for that down here. So we're after 3 root 3 over 2. Was it p squared minus 1x squared? Yes, p squared minus 1x squared. So this is what I'm aiming for. So this is my thought bubble. I'm thinking I want to just get this somehow. I'm just going to box it off there. That's my target. So here, you can see that 3 root 3 over 2 are factors of both of these. So we can factorise out the 3 root 3 over 2 straight away. So the first one, after 3 root 3 over 2, we've got p squared x squared, then minus the same thing times x squared. So the first step would have that in brackets. But of course here, you can see we can factorise out the x squared from these brackets as well. So 3 root 3 over 2. What goes into brackets now, if I factorise out the x squared, is these terms divided by what I'm factorising out. So p squared x squared divided by x squared, that'll just leave us with p squared here. And then the minus x squared divided by itself. Anything divided by itself is 1, so this is going to be replaced with minus 1. And that's what we wanted to prove all along. So we've proven what we needed, therefore we've completed the question as required. Let's have a look at the next one. Luckily, this is a 1-mark question. This is absolutely horrid what they've done here, in my humble opinion. You've been given a list of 5 numbers. This really gets you thinking, or crying. 98 to various powers. You need to find the lowest common multiple of these 5 numbers. Well, because each of these has 98 as factors, these are all factors of 98, you could get them all to be 98 to the power 91. So actually the lowest common multiple of all of these, and I'll explain a bit more in just a moment, the lowest common multiple is just simply 98 to the power 91. So that's your answer. If you want to skip ahead now, fine. But if you want to hang around for a couple of minutes, I'm just trying to explain why this is the case. Let's imagine this with being an easier number. Let's imagine it's 2's. So let's imagine, what's the lowest common multiple of 2 to the power 4, 2 to the power 3, and say 2 to the power 1? Well, if we could, not that we can here, we could have worked these out. So 2 to the power 4 is 8. No, it's not. Grow a brain, Mr. Bailey. 2 to the power 4 is 16. 2 to the power 3 is 8. 2 to the power 1 is 2. The lowest common multiple of all of these would have been 16. 16 is 16 times 1. I can go from this 8 by timesing by 2. And 2 I can times by 8 to get 16. So because all these bases are the same, we can just multiply the smaller ones by a certain multiple times of the base to get it to the big one. So here, I can times that by 2 to go from 2 up to 16. I can times by 8, which is timesing by 2 cubed. In similar ways here, I can go from this to that by multiplying by 98 to the power 3. Remember, when we're multiplying, we add the indices. 88 plus 3 gives 91. This one again, same idea. I could just multiply that one by 98 to the power of 18, because 73 plus 18 would give 91, and so on. So that's why it's simply 98 to the power 91. It's a hard thing to get your head around. A fairly weird question in my opinion, but original for definite. Now let's move on to the very last question on the entire paper. So, number 21. We've got this equation, 5c plus d equals c plus 4d. We are now asked to find the ratio of c to d. First of all, what we need is to get one as the subject and in terms of the other. So first of all, what we could do here is subtract d from both sides. So if we take d from both sides, what we'd have is 5c equals c plus 3d. If I then subtract c from both sides, I then get that 4c equals 3d, and then finally I could divide by 4, and if I do that, I'd get that 1c is simply 3/4 of a d, or 3d divided by 4. What I'm wanting though is the ratio c to d. So what I actually want is this ratio here from c to d. So I know that c is 3d over 4, so I can replace c with what c actually is. So c I've worked out as 3d over 4, and d I can leave as d. So this is the ratio in its horrible form. We should try and simplify this now. So what I can do on both sides, I could divide by d on both sides, essentially to cancel out the d's. So 3d divided by 4 over, so divide by an extra d, that'd cancel to just give 3/4. Over here, d divided by d would just give 1. Now ratios are simpler when both sides of a ratio are in terms of whole numbers. So here, I've got quarters. How can I undo quartering something? You can multiply by 4 instead. So final step, we can multiply by 4. So we get 3.4. So therefore, c dot d is simply 3.4. Part B is where it gets very interesting. So we've got this here, which is a quadratic in disguise. X and y are both positive. We need to find the ratio of x to y. So the first thing we're going to do is to rearrange this one. Get everything onto the side of 6x squared. So subtract 7xy from both sides. And finally subtract 20y squared from both sides. After subtracting 7xy and 20y squared from this side, we get that it's all equal to 0. Now it doesn't look like it, but this is actually a factorizable quadratic. So there's various ways of how to factorize quadratics where you've got more than 1x squared. So please forgive me if I need to teach you this one way, but the teacher can help to explain this, if not myself. This is my method. Treat it as a normal single x squared by taking this n number and multiplying it by the other end value, which has nothing to do with the x. So think of it as x squared minus 7xy minus 120y squared now. The next thing I'd be saying, if it were a normal quadratic, is to be finding two numbers which multiply together to give minus 120. But now, I need to find two values that multiply together to give minus 120y squared. And in normal circumstances, I'd be saying these two numbers need to add together to give you minus 7. But now, we need to add together to give minus 7y's, because we've also got a y mingled with this x now. So treat them as numbers first of all, then just tag a y at the end of them. So what two numbers would multiply together to give minus 120, but add up to give minus 7? Well, the two numbers that would work there would be 5 and it would be 8 and minus 15. So we could have 8 and minus 15. However, because it wasn't just minus 120 and minus 7, it was involving a y, we have to add on the y. So 8y times minus 15y would give minus 120y squared, and 8y plus minus 15y would give minus 7y as well. So these are our two values we put into brackets. So we do x plus 8y in one, and in the other, x minus 15y equals 0. But of course, this 6 disappeared. I just made it vanish, but you can't really do that. We need to put it back in. The 6 goes back underneath each of the terms with nothing to do with x. What we do next is simplify these fractions if we can. So 8 over 6 we can simplify. 8 sixths simplifies to 4 thirds. So I can call that 4y over 3. And 15 over 6, I can divide 15 and 6 by 3. So that simplifies to 5y over 2. So next what we're going to consider here is the fact that these are still fractions with still non-unitary denominators. So what do I do with that 3? What do I do with that 2? Well, what you do here is you just shift any bottom number in front of the x instead. So that becomes 3x plus 4y. The same here, just move that 2 in front of the x, because 5 over 2 doesn't go any lower, to give you 2x minus 5y. So the next thing we have is 3x plus 4y, brackets 2x minus 5y, equals 0. Now, we're told here that x and y has to be greater than 0. So if you've got one bracket times by another, either the first bracket is equal to 0, so maybe is it 3x plus 4y is equal to 0? If that's the case, then subtract 4y from both sides, we'd have that 3x equals minus 4y. So let's think about that. If x were positive, like say if x were positive 10, 3x would be 30. Then y, if 30 equals minus 4 times something, that would force y to be the opposite sign. So if x were positive, y would have to be negative, or if x were negative, that would make y positive. So this is impossible if they both have to be positive. So actually, this bracket here isn't going to be where our solution lies. We therefore have to consider this case, but it must be that 2x minus 5y equals 0. So get x in terms of y, so 2x equals 5y by adding y onto both sides. So then we have that x equals 5 over 2 lots of y. So we want the ratio of x to y, so what we can say now is that therefore x dot dot y, well I know that x now is 5y over 2, or 5 over 2y, whichever you want to think of it as. 5y over 2 I'll go for. I'm going to leave y as y. We can now, like we did for part A, simplify this ratio down. So we can divide both sides by y. So 5y over 2 divided by y just gives us 5 over 2. Y divided by itself, just like anything divided by itself, gives us 1. Then finally, to simplify fully, we can get rid of those bottom numbers. We can multiply both sides by 2. So 5 halves times 2 gives us 5, and 1 times 2 gives us 2. So that's part B of the final question on the entire paper. So that concludes this session. That probably felt like an awful lot to get through, but thank you for listening, even if it was to only a few questions. I hope those have helped you in some way. If not, do find me, say hello, or drop me a comment here. Please do like and subscribe, so now I'm not just talking to myself for no reason whatsoever. It is nice to know that, you know, I am helping people. So once again, thank you for listening, and be in touch soon for the next video. Take care, and you'll hear from me soon.